He was out there, it comes up, I mean, it's gotta come up.
207 maybe?
You know, I usually time
We're
it.
trying that, I'll be right
That
back.
was my
No,
race.
it was like-
That was your race. Well, how does that time hold up?
Never did anything.
Yeah.
30% snow.
Not good enough for varsity. That's a JV time.
Doesn't matter how much it's.
I think it's okay.
Yeah.
We'll get the report.
Well,
if you want, before line, just.
Yeah, right.
Okay.
No, they'll be staring at these chairs. That's okay.
Wherever I'm told.
They'll see whatever's on the screen.
With the lack
Because, yeah, I shared your blog with her, she left, and that was on Monday. So she
Is it down to 1,000 now or even that?
Yeah.
Is it even there? It's less than that?
Right.
But she.
It's gonna be a workout.
Much. No, some people are trying to, one guy, this weekend, 900. So I think.
Okay.
Yeah, warm days, maybe.
Oh, West.
Jeff Hennessy and Kirk Bachman, those guys were gonna go last Saturday, I think.
Yeah, right
It's,
there.
you're saying that that was not an argument, so it's redo the
Oh,
password. Yeah.
That's called.
It worked for you, but then it's not.
I think it was 800. My old 13 and a half.
You know.
Yeah.
That's what I would take.
Back in those drought years in the late 80s or early 90s, I did, a lot of events where I was like, I'll do a few games or something. So, well,
But no, the one guy was asking,
yeah.
I said, I've done it twice. Nine hundred. It's always busy.
But that's better.
Because the first half of the trip last time, I should put James there.
It's cheese, it's so easy, yeah, and then beautiful. Yeah, and then you get it 5 minutes.
No, it's.
Oh, okay.
I never eat much breakfast that morning, I'm always nervous as hell.
Because the one guy said, yeah, you gotta watch out for lines, rapid, 5 on. Well, which one last one? I think that's easy. Well, but I thought, sure, and they don't redo it because we came first, so they're.
In there,
Yeah.
against that wall?
When we start, probably ought to do a roll call
Oh,
for
that's a
the
different one.
Yeah.
committee members and other board members.
So George, when he came out of his cab, I would have like, my spine there. Yeah. And he.
Got a fair amount.
Because you couldn't.
Oh, okay.
Right.
But I would
I've never really done it at that point. I did it 1 year, at triple. Overnight,
Yeah.
3,600.
Oh, yeah.
I was American, I touched on it. That was nothing, couldn't recognize anything in the. But you were, yeah, it was still classic. Yeah.
All right.
You know, Day 3, we're just camped right up. Just rained like hell up in Traverse Mountain or something. I was like, well, I got across 2 days. Got up at like 5 minutes. I was kudos to the floor there. It was like, Stupid, get up. We gotta rescue some shit. But anyway.
No, we, it rained just 3 quarters. Wow. I gave her my questions. Who put water in the rain? She says, no, but you. But luckily it snowed in Charlotte. I don't find.
Yeah. You know, the place in Ivy's like 8 feet tall when you come into 5 miles, and all of that place in Ivy is water. I'm just like, holy crap, I just don't recognize anything.
Yeah, we had done it over.
Morning in progress.
That's when I got sleep. So. When I was at the subway last week. And I came back about 20 minutes later. I was like, oh, I see all this.
Still rating up there, it's just all heat. Yeah, like that's when they're operator. Yeah, I know. I just have zero.
I see. I'm with this, I don't know. Trails. Was it really? Oh my God. And that's a long.
Did the horses have some of your weight? They saw it.
Yeah.
Yeah. Food and everything.
Wow. But it took 6 hours, 20 minutes. Both ways. And there's mountains of air levels, so it just cruised. Bring for your, they like to live, you lose your whole bottom plate. But I was going to do like Raybould trip.
Okay, we're going to call this Cloud Seeding Committee meeting number 1-25 to order. This meeting is originating at the Idaho Water Center and is being streamed on YouTube. First of all, I'd like to excuse Chairman Gibbs. He is not able to be here today, and I, Jeff Raybould, will be chairing this meeting. With that, Jennifer, maybe we could have a roll call vote with committee members and other board members present.
Absolutely. Mr. Gibbs is absent. Mr. Barker,
Here.
Mr. McMahon,
Here.
Mr. Raybould,
Here.
Ms. Cole-Hansen,
Here.
Mr. Olmstead,
Here.
Mr. Stevenson, absent. Mr. Van Stone. I see Dale's online.
Okay, all right. Okay, with that, we have a quorum. We'll move on to the next item on the agenda, which is a cloud seeding season update. Mr. Patton, how's it over there?
Kayla Golden with staff will give that cloud seeding update for this past winter season.
Great. Good morning, Mr. Chairman, members of the board, and guests that we have in the room today. My name is Kayla Golden. I am the Water Resource Board's Program Manager. And I'm going to be providing a brief intro on our program as well as a season update before we turn over the majority of our time today to our technical presenters for some information on cloud seeding. So high level, I'm going to give a very brief background, summarize our operations in Idaho and current projects, and then we'll move into our technical presenters. We have about 4 or 5 of them that will be speaking today on the science and history of cloud seeding, some of the operations and how they work, some of the environmental considerations with regard to cloud seeding operations, as well as some of the frequently asked questions that we get. So really briefly to start, what is cloud seeding? Cloud seeding specifically is a method of introducing aerosol particles into an existing cloud to generate ice formation. And precipitation enhancement is a form of cloud seeding that we use here in Idaho to augment winter snowpack, our primary water storage reservoirs. And so the objective of cloud seeding that we do here in Idaho is specifically for precipitation enhancement. And it is to support the long-term water sustainability of our water supplies here in Idaho. So high level, this map produced by the USGS just gives you a rough idea of the primary water uses across the United States. I've overlain that in the top left-hand corner with a map of the various different states that do cloud seeding. So you'll see that largely in the areas that we do cloud seeding are primarily areas with pretty heavy irrigation and water use, and mostly centric to the Western US. And so we'll be hearing a little bit more about the different types of cloud seeding in our following presentations. But again, here in Idaho, with irrigation being our primary water use and demand, that is largely one of the reasons that we started conducting cloud seeding here in Idaho. So summary of our current operations here in Idaho. We have a number of different project sponsors and operators across the state. Cloud seeding is only conducted in the southern portions of the state. We have a few different projects in the Central Mountains region that generally covers the Payette River Basin, the Boise River Basin, and the Wood River Basin. And then we also have some projects in eastern Idaho, as well as some that are operated by the state of Utah currently in the Bear River Basin. And so our collaborative program is a program that is sponsored by the Idaho Water Resource Board in partnership with Idaho Power Company, who operates this programs. And we also collect or get funding support from water districts via water users in the state as well. Eastern Idaho projects, we have a long-standing manual generation cloud seeding project that has been in operation since the 1990s. That is sponsored by the High Country RC&D and operated by Let It Snow. And then North American Weather Consultants is Utah's, state of Utah's operator that currently has some infrastructure in the lower portion of our state. And so we'll get some more information on the different types of cloud seeding equipment and how they're used. But here in Idaho, we have a number of different instruments that are used for cloud seeding, primarily being remote ground generators. We do have some manual ground generators, as well as aircraft that utilize both burn-in-place flares and ejectable flares on aircraft. So all of our projects are also supported by a number of different weather instruments. These are necessary for forecasting and guiding our operations, and as well provide us with data that we utilize to analyze the projects. So this table gives a very high-level summary of cloud seeding in terms of the state's participation. Again, cloud seeding operations have really been occurring in the state of Idaho since about the 1950s. And the bulk of those were largely manual generator projects that were locally sponsored, locally operated. And then we saw consistent operations really start in East Idaho in about the 1990s with the High Country RC&D project. And in 2008, that's really when the state came to this table and started discussing cloud seeding. And that was really as a mechanism to support the Eastern Snake River Plain aquifer. And so this aquifer is one of the most fertile in the world, serving over 2 million acres of irrigated agriculture, which contributes roughly $40 billion to our state's economy. And so water is obviously highly necessary for agriculture. And so given the declines in the aquifer, cloud seeding was brought to the table as a mechanism to support long-term water supply sustainability. And so really the idea at that time was that it was proposed by Idaho Power Company, who had already been operating projects in the Payette River Basin, that potentially we would operate a pilot project in the upper Snake River Basin to support the aquifer. And the idea was that if it was successful, then the state and water users would come on to fund the long-term operations. And so that's exactly what happened. That project was deemed successful, and it has been continuously operational since about that time. Given the success in that basin, water users in the Boise and the Wood River Basin, who are also highly dependent on water supplies, approached Idaho Power Company about starting projects in those basins as well. And so today, the Boise River, the Wood River, and the Upper Snake River Basins are all operated in a collaborative partnership operated by Idaho Power Company. So since that time, you'll hear more about the Snowy Research Field Campaign. This was some groundbreaking research that really demonstrated the efficacy of cloud seeding, that it can be used to generate more precipitation. And so from that point, the board began investing in tools and technology to really assess the water output that we're getting from cloud seeding. And so that's a lot of the different modeling efforts that you're seeing in the orange. The board has been continuously working on an analysis project for several years now, independently and supported by the National Center for Atmospheric Research. And so this analysis project, I'll give a very high-level summary of, is intended to help the board understand what are the impacts of increased water supply and how might cloud seeding benefit our water supply here in Idaho. So 2021, there's a note here on the top of the timeline, was really when the legislature first deemed that the Idaho Water Resource Board would be responsible for oversight and management of cloud seeding here in Idaho. And really what that means is that the board has the authority to authorize projects here in Idaho and ensure that they are following safe practices. So this legislation did also provide the board a mechanism to fund cloud seeding operations to support water supply sustainability. And the board has conducted a few different research projects in some other basins to support that effort. in response to that legislation to support other basins. So high level on our cloud seeding analysis, again, you'll hear more about some of the science behind this and why we believe it works. But fundamentally, we know that more precipitation will result in increased snowpack, and increased snowpack will generally result in increased stream flow. And so we know cloud seeding works as a result of the 2017 Snowy campaign, which you'll hear about next. So largely the analysis that we've been working on aims to answer, one, how much additional precipitation do we produce through cloud seeding? That's really step one in evaluating the benefits of cloud seeding. Step two to that is then how much water did the increase in precipitation add to the system? And so when snowpack starts to run off, it's not necessarily a one-to-one relationship. You're going to lose some of that to evapotranspiration, groundwater saturation, plant uptake. There's a number of different variables that result and ultimately determine how much water will make it out of the basin. And so that's really step two of our analysis, is understanding how much of that increased supply actually makes it to our streams and rivers. And then number three, of course, is where does the increased supply go and how does it benefit our systems? And so step three is really where the state is at right now in determining how increased supply affects the system. However, the board has partnered with Idaho Power Company and the National Center for Atmospheric Research to develop a cloud seeding model that will ultimately help us to better understand our increases in precipitation. And this model is also used for guiding and forecasting operations, which you'll hear about a little bit more in some of the following presentations. The other investment that the board has made is into the development of a hydrologic model that couples with atmospheric processes. So again, that I mentioned, once that snow starts to run off, it's subject to a number of different variables. And the board is working on developing a very unique model that will ultimately help us understand how much of that water makes it out of the basin. But high level today, I'm just going to provide you a brief summary of the results that we found so far on generally what does increased supply do to our system. And so answering that really requires two questions. One, can we model the system before cloud seeding? And then how sensitive is that system to change? And so in other words, if we turn the dial and add a little bit more water to the system, how does that affect the hydrology and water use within the state? And so to do that, we are using what's called the Snake River Basin Planning Model. This was originally developed by the Bureau of Reclamation, and Idaho Power has also taken a copy of this and integrated Middle Snake Reservoir operations and recharge. They do this primarily for their IRP and analyses. And then the Department of Water Resources has also obtained a copy of this same model that we've been utilizing to analyze cloud seeding and recharge. And so key thing I want to highlight is that this model allows multiple different agencies to work together as a sort of a collaborative tool on water management. So we're not necessarily comparing apples to oranges anymore, but maybe like green apples to red apples. So tools that allow us to analyze water supply in a very similar way. And so I'm only going to show a couple of different slides from this analysis. We looked at both long-term and short-term effects of increased supply, but really you can see the bulk of more of the effects when you look at things in the short term. And so what you're looking at here is a chart of our water supply in the Snake Basin, and generally that red line is what we're using to determine more of a dry year versus more of a wet year. And so a dry year being when we don't quite have enough water on the system to meet all of our water supply needs. And a wet year generally being something above that red line when we have more than sufficient water supply to meet needs. And so this just gives a very high level summary and a great visual on how increased supply ultimately affects our system. Generally in some of those wetter years, like you would have seen in 1995 to 2000, cloud seeding really doesn't have as much impact as it does in some of the more dry years, which you see in the later half of the 2000s. But looking at this table, I mean, we've really identified impacts to diversions, recharge, some of the benefits to hydropower, but some of that out of basin use, I think it's critical to understand that these also increased water supplies affect our fisheries, they affect water quality, they affect recreation. So there's a number of different benefits to increased water supply that aren't necessarily captured on this table. But the long and short of this is that it's incredibly useful and beneficial in some of these dry years, like we would have seen in 2001 and 2005, for example, when increased water supply on the system would have been highly valuable and highly critical to our systems. So long and short, what are the benefits of increased snowpack and subsequent stream flow? Well, there's a lot of them. So increased snowpack, as I mentioned, is what we use cloud seeding for. that starts in the mountains. We have a significant amount of recreation in the winter time, so increased snowpack obviously benefits that. As that water starts to melt off, you'll see a lot of that benefit to groundwater, to plant uptake, high mountain streams that support critical fisheries. Moving on down the system, you'll see benefits to our water supply needs. We utilize that for storage and reservoirs, irrigation, managed aquifer recharge. Going down the system, that water is very valuable for hydropower, which is useful in decreasing energy costs, as well as water quality and important fisheries that we have along the Snake River system. So with that, I'm just going to briefly summarize this past year of operations. So our typical operations here in Idaho run from November 1st through April 30th. We have 4 different projects, like I mentioned, the Idaho Collaborative Cloud Seeding Program, which consists of the Boise, Wood, and Upper Snake River Basin. However, this project is operated in coordination with the Payette River Basin Cloud Seeding Project, which is operated independently by Idaho Power Company. And so in total, the total infrastructure that we have for the collaborative is about 52 remote ground generators, 3 aircraft, and then a network of weather instruments. And those 2 areas are highlighted in the blue and the orange circles over there on the left. And then we've got a summary of the total hours for different types of infrastructure for that program. And so you will also hear a little bit more about this program in some of the following presentations. A brief summary of our High Country RC&D program. This program is operated in eastern Idaho. It sort of overlaps with our collaborative basin project and consists of about 25 manual ground generators with forecasting support from Idaho Power Company. And this one is operated by Let Us Know. And so their total hours of operation for manual generators this season, and again, that's between the entire period of November through April, is about 1,415 hours. Northern Utah, like I mentioned, does have some infrastructure in our state. If you'll notice, it's just a few generators that they have over the border. And so some of the numbers that you're seeing here are a summary of their total project there in the green. They only have about 3 total manual ground generators here in Idaho, and that one is operated by North American Weather Consultants. Lastly, I do want to cover, the board has started investigating the potential use of liquid propane as an alternative seeding agent. So liquid propane can nucleate ice or create more snow at a warmer temperature. It doesn't necessarily rely on winds going over a mountain, which you'll hear a little bit more about how that works with our AGI generators. And it's generally cheaper to operate. And so that's the reason that the board has invested in partnership with the state of Utah into a research project or investigation of liquid propane to understand how we might be able to use liquid propane for cloud seeding. And so this past winter was actually the first time that we had a liquid propane generator operational for this project. And we saw about 11 total seeding events from December through March, with 9 of those storms being seeded. And so this project is largely focused on data collection. So the list that you'll see on the left includes a lot of the different data points that we're collecting. We have about 35 to 40 different weather instruments out across the Little Camas Prairie. And again, these are largely focused on collecting data to help us understand how liquid propane could potentially be used for cloud seeding in Idaho. So the last thing that I'm going to wrap up here is a brief walkthrough of our website. This is a great resource for information on cloud seeding if you're curious about what's going on in the state of Idaho. So this website does cover existing operations, whether projects are operational or not. It has a lot of the different science and information, all of our project reports and documentation that the board asks for from our operators. You can find those on our website as well. And really briefly, I'm just going to walk you through a couple of that tabs so folks know where to navigate and to find these. All right, so landing on our homepage, if you're looking for information, let's close this a little bit. But generally, you'll see right from the top when cloud seeding is operational. So typically in Idaho, our aircraft operations run from November 1st to March 31st. And we'll have ground seeding operations that will go from November 1st all the way into April 30th. And so on our webpage, you can find a lot of the frequently asked questions on silver iodide, on what we're doing with liquid propane research. some of our monthly and annual reports. And typically when we're in season, you'll see these gray boxes over here will turn active with green or yellow if they are suspended. And you will hear about what that means in some of our following presentations. And so something I do want to highlight is that generally when you see these say active, that doesn't necessarily mean that cloud seeding is actually happening at that time. It just means that our operators are forecasting for storms that may provide the conditions for cloud seeding. And so typically you'll just see those green during the November 1 through March timeline. So down here is where you can navigate to a number of different tabs. By clicking on these, you can go through things like the history of cloud seeding. There's a lot of good different information on that tab. You can as well find a lot of different information on the science of cloud seeding, why it's used. And a lot of this is stuff that you're going to hear about today. But if you'd like to go through and navigate our website on your own time, I would encourage folks to do so. So we've also got a lot of information on the different research projects that the board has invested in. You'll find this same table that I just saw. There's quite a few different projects, both related to research and modeling that the board has invested in. And you can read more about those projects here on our website as well. So we do have a tab on here as well for program administration. This covers House Bill 266 and all of the different statutes and pieces of legislation that apply to cloud seeding in Idaho, as well as the current authorizations for different operators that we have in the state of Idaho. Lastly, the last tab that I'll just make folks aware of is the documents on our seasonal and monthly reports. And so we went all the way through April 2025, that is last month. And if you'd like to see what our different operators are doing in the various different basins, you can also find that information on our website. And so, Mr. Chairman, that's all I have for you today. I'm going to wrap up and turn things over to our presenters for some technical presentations on the science.
Okay, committee members, any questions for Caleb? Okay, other board members, any questions? Okay, I think we're good to proceed to the next presenter.
Okay, Mr. Chairman, now we have a series of informational presentations. And first up is Dr. Sarah Tessendorf from the National Center for Atmospheric Research.
Good afternoon, Mr. Chairman. Can you hear me?
Yeah, we can hear you very well. Welcome.
Okay, and can you see my screen? I'm going to try to get it into slideshow mode.
Yes, we see it.
Okay, so, and I hope you see the full slide, because I just changed the
Yes.
display. All right. Thank you so much for having me. My name is Sarah Tessendorf. I'm a scientist at the U.S. National Science Foundation, National Center for Atmospheric Research, otherwise known as NSF-NCAR. We're based out of Boulder, Colorado. I'm here to briefly talk about the science behind cloud seeding, especially how it works and some recent advances that have been made. Just up front, I wanted to walk through some of the key messages that I'm going to try to explain here. The first one, as Ms. Golden has already described, cloud seeding is a technology that aims to enhance precipitation. And I'm going to walk through the physical conceptual model for how that works. We've also had recent scientific studies that have proven that cloud seeding works to enhance snowfall in winter storms over the mountains. And I will also present the evidence for that. We have also made advances in our computer modeling capabilities that we're using to help quantify the impacts of cloud seeding on precipitation and streamflow. And Ms. Golden described several of those. And so that's a key point that I want to point out as well, because that's one of the reasons that the science has come a long way in just the last couple of years, even though the concept of cloud seeding has been around a long time. And another point is that cloud seeding effectiveness will vary storm to storm and location to location. It's not going to be the same everywhere. And so it's also really important that feasibility studies are conducted prior to embarking on any cloud seeding program. So this diagram walks through the conceptual model for cloud seeding a winter storm that forms over the mountains. The number one step is that there's a cloud, and the clouds over the mountains often form because the air, as it flows up and over the mountains, it cools and allows the condensation process of the water vapor in the air to create that cloud. But beyond just having a cloud as the first step, we also need that cloud to have specific characteristics. And especially the number one key ingredient here is that that cloud needs to contain supercooled liquid water. Supercooled liquid water is liquid that is existing at temperatures colder than the freezing point. So the freezing point is 32 degrees Fahrenheit or 0 degrees Celsius, depending on which temperature scale you like to use. Liquid water does not always immediately freeze when it reaches that temperature because it needs a particle to freeze on. And so in many of the clouds in the atmosphere, especially between 32 degrees Fahrenheit down even as cold as 10 degrees Fahrenheit or even colder than that, can have supercooled liquid in the atmosphere in those clouds. That supercooled liquid poses a hazard to aircraft as they fly through. You might have been on an aircraft that got de-iced and has de-icing fluid to prevent that liquid water from forming on the aircraft when they're taking off. Aircraft are also navigated around clouds in winter in order to avoid hazardous icing conditions. So one of the other things, though, when a cloud has that supercooled liquid water in it, is it's a sign that the cloud is not as efficient as it could be at producing snow because it's not producing ice readily yet. So naturally in the atmosphere, once we get colder than 10 degrees Fahrenheit or minus 15, minus 12, minus 15 Celsius, we have particles in the atmosphere like dust that serves as pretty effective particles for ice to form. But we also, back in the 1940s, discovered that there are other materials that can form ice. And silver iodide is one of the ones that is used most commonly because it's been shown to form ice as warm as about 23 degrees Fahrenheit or minus 5 degrees Celsius. So there's this window where you can actually create ice in the cloud with these additional particles to help enhance the precipitation formation. So that next step is you release the silver iodide seeding agent. It's often done by ground-based generators or by aircraft, as shown in Ms. Golden's slides. She showed a picture of a ground-based generator as well as the aircraft. The next step is that these particles need to get into the cloud. An aircraft can release them often right in the cloud, but for a ground-based generator, we want to make sure that the wind flow is right in order to carry those particles into the cloud. And then when they're in the cloud and they're at temperatures colder than about 23 degrees Fahrenheit or minus 5 degrees Celsius, they form ice. That's the fourth step. And in the atmosphere, once ice forms in a cloud that has supercooled liquid water, it can rapidly convert that supercooled liquid water into larger and larger ice crystals or snowflakes. And so that's that final step, is that additional water is converted into additional snow. So that's the overall science behind how we're creating additional snowfall with the addition of these particles from a cloud seeding process. So as I alluded to, this concept has been around for quite a while. It was initially discovered in the 1940s, and there was a lot of excitement about it at the time, especially when this photograph was published in Life magazine, showing that proof of concept that this liquid cloud layer, supercooled liquid cloud layer, once in this case, it was seeded with dry ice, but that dry ice then converted that liquid into ice and depleted the cloud there. The challenge was that was the initial step. That was kind of the first half of the conceptual model. But then the rest of it, measuring the amount of additional precipitation reaching the ground, posed a lot of challenges. And part of that is because some of the clouds that we're seeding do already produce some amounts of precipitation, and we're trying to enhance that process. And so one of the ways that this research was done was using statistics. And those statistical evaluations were often done similar to a pharmaceutical trial, where you treat some of the clouds, but you don't treat the others, and you look for the differences between those populations. And in order for that to really be conclusive, though, we need the variability in the sample to be pretty small, or we need a really big sample of storms to be seeded and not seeded to do the statistics. And the challenge is that in nature, precipitation is highly variable. And it was so much more naturally variable that we couldn't detect and easily distinguish the signal from seeding, which was thought to be smaller than that natural variability at times. And so a lot of the statistical studies were deemed to be inconclusive just because that that gold standard for statistical evidence that showed with high degrees of certainty that the effect was due to seeding wasn't met. That's not saying that it wasn't working. There were signs in these statistical studies that there was an effect from seeding. It just wasn't at statistical significance levels. And so you couldn't really tell without any doubt that it was happening, but there were signs that it was. Fast forward to 2017, we were in the field doing a field project called SNOWY. It stands for the Seeded and Natural Orographic Wintertime Clouds, the Idaho Experiment. This experiment was the first time that we were readily able to detect the impact from cloud seeding. And the reason we were able to do that was because we were seeding with aircraft. And when an aircraft flies back and forth across a straight line track, the seeding material will disperse downwind in a zigzag-like pattern. And we were able to detect that zigzag-like pattern on the radar in selected cases where there was no ice or snow forming naturally in the cloud. And so that's what you're seeing on this animation here. This is a radar image over time. The aircraft was flying along the yellow track that shows up in the first half of this animation, so it'll come back on. The aircraft location is actually the orange dot. So if your eyes are good enough, you can see it's kind of bopping back and forth along that line. And we're looking at the radar reflectivity from a radar that we put up on top of the mountain so that we could see these low-level orographic clouds that form over the mountains in an area where the normal Weather Service radar called NEXRAD cannot see because the mountains themselves block the NEXRAD signal. So we're, the NEXRAD is down here in Boise, and we're looking up here just over the mountains in the Payette River Basin. And so this aircraft is flying back and forth across this yellow line track. The winds are out of the southwest, dispersing the material downwind, and you can see that zigzag-like pattern shows up. Another reason that this was really crucial evidence that this was from the cloud seeding is a few of the flight legs were flown with ejectable seeding flares that are released every 30 seconds as the aircraft flies. And when those seeding legs were flown, you'll see here a dotted line pattern coming up right about now in a few of these flight legs. So it was even more evidence that this reflectivity pattern that we're seeing is from the seeding material being released from the aircraft. This was a huge breakthrough in this field to be able to detect with the radar the seeding pattern. And we were able to trace these reflectivity patterns from the radar to the ground. We had snow gauges around the area in the squares shown in the map. We were able to then see when those seeding lines passed over the gauges, the increase in precipitation at the gauges reaching the ground. So we were able to, for the first time, quantify in magnitude and over a spatial area using observations, the impact of cloud seeding. We saw this pattern with these very clear zigzag patterns, these line patterns, in 3 cases right after the field project. They were very obvious because there was not a lot of background ice and snow in these clouds. So the radar reflectivity, if you see it here at the beginning, there's not much reflectivity on the radar screen. And so that pattern just stands out very, very easily. Since then, so we collected data in 24 cases, 21 of those were seeded. And we saw this in 3 cases right away. Since then, over the last several years of doing research, we've been able to detect the seeding line pattern in a few more of the cases. In the rest of the cases, what's happening is we have ice and snow already forming naturally in the cloud. So the radar data is more cluttered just due to the natural patterns that are there. And so it's really not easy for us to see the enhancements and the pattern in particular on the radar when we have cases like that. That doesn't mean that there's not an effect happening. It just means that we can't observe it with a high confidence on radar. And so that's where we're using other capabilities like the new computer models to simulate the impacts of cloud seeding to help us better understand the impacts that are happening in those cases as well. So this was a very big deal for us to prove that conceptual model, that entire conceptual model of snowfall actually reaching the ground with the SNOWY data. And I want to just point out too, the Snowy project was on the heels of some other work that had been done. We had a lot of support from Idaho Power Company. Prior to that, we had a lot of new research on cloud seeding coming out of the state of Wyoming with their Wyoming weather modification pilot program. And so, the timing was right to really bring some new observational capabilities and some new science into addressing this longstanding question of, does cloud seeding work? And so coming out of Snowy, we can say, yes, cloud seeding does work, but we also have additional questions that we still need to answer. One of them being, when and where does cloud seeding with silver iodide work most effectively? Because again, not every cloud is going to be exactly the same. They're going to vary from storm to storm in how it's naturally producing precipitation, as well as how much additional precipitation cloud seeding could even provide. And so, what we're seeing in Snowy is some of that variability from case to case. And we're doing some computer modeling now. We want to better understand that because that will help guide and determine which storms are the most seedable, which ones should be the ones targeted. We're also starting to look into liquid propane, like Kayla pointed out in the presentation before me, as another method for cloud seeding. We're still working on how do we confidently quantify the impacts of cloud seeding. We're not going to be able to see that radar pattern in all the cases, like I mentioned. And so this is where using computer modeling is important, but computer modeling has its own sources of uncertainty. So we're trying to do a combined approach using both computer models and those advances there with observational capabilities, having some instrumentation and observations from the field to address these things together. The other couple questions, how does cloud seeding impact snowbelt-driven stream flow? As Ms. Golden described, stream flow is often one of the key outputs that cloud seeding is being used for. And so getting from the precipitation to the amount of extra water in the streams is another component that we're building some computer modeling capabilities to address. And then to get a good quantification of the impact of cloud seeding is important for us to then address how cost effective is cloud seeding to augment the water resources. So these are still questions that we're working to address. And I'll, at the end of these technical presentations, circle back to this a little bit. But in the meantime, I want to also point out we have developed, with the assistance of the Bureau of Reclamation, an online training module it's about 45 minutes long. It's free. You do have to sign up for an account to get access to it through the COMET website. But the COMET program is a well-known training program that has all kinds of online training modules for weather-related topics. And we have one now for how cloud seeding works. The QR code, if you scan it, will take you to the website as well. So if you're interested in learning a little bit more, that training module is also available. And then I'm just going to circle back to my key messages before handing it off to the next presenter in this lineup. So again, cloud seeding is aiming to enhance precipitation, and that's how it's being used here in the state of Idaho. We've had these recent scientific studies, like from Snowy, that has proven that it does work to enhance snowfall in winter storms over the mountains. And we're now using advances in computer models to help quantify the impacts of cloud seeding on both precipitation and stream flow to continue answering some of the key questions that remain. And one of those key questions is related to cloud seeding effectiveness, because we know it varies storm to storm and location to location. So we need to really do our due diligence to make sure that there's feasibility studies before embarking on a new cloud seeding program, and then use that new knowledge to help guide targeting for cloud seeding operations as well. And that will be all I'm going to cover for now, but I will be speaking again at the end of this session. So, thank you.
Okay, thank you, Dr. Tessendorf. Committee members, any questions? Other board members? Okay, we'll proceed to the next presenter, Mr. Patton.
Okay, next presenters, be a joint presentation on cloud seeding operations. This will be given by Sean Parkinson with Idaho Power Company and Bruce Bowe with Weather Modification International. And there's Mr. Bowe.
Okay, Mr. Bowe, welcome.
Thank you. I'm going to share my screen here for a bit, and then Sean will follow up. I've got about a dozen slides or so. So if I can pick the right one, I think we're there. And you should see a presentation anytime here. Is
There
that
it is.
visible?
Yes, we have it now.
Very good, thank you. I've got about a dozen slides here. What I'm going to speak about is, of course, how it's done procedurally. My comments are not going to be limited to strictly how it's done in the Idaho Power Program. Dr. Parkinson can address that if he chooses, but rather how, in general, winter orographic cloud seeding is done. Ms. Golan already showed you this graphic with a minor difference. Her version has the program that's relatively new in New Mexico on it. And this version, which I downloaded from the North American Weather Modification Council website yesterday, for some reason did not have it. But the reason I'm putting it in here is because I wanted to share with you the fact that there is interest in starting a program in Western Montana adjacent to the Idaho programs. There's also interest in a feasibility study ongoing in the state of Washington, in a irrigated area near the Cascades, and yet another program in Oregon. There's interest in all three of those states in starting programs. I know the National Center for Atmospheric Research has been involved in those. I will not offer comment on the nature, how far those have come yet. But I wanted the board to be aware that it's almost all of the western states. The exception is Arizona. They're actually lower Colorado basin states, and they're already funding weather modification in upper basin states. So there is, in a sense, activity there as well. The ways that we recognize when we have an opportunity to see clouds are multiple. Some of these you've already seen. Ms. Golden showed some indications in her slides that talked about some of these things. One of the things that we do on a fairly regular basis is look at atmospheric soundings. The Weather Service does soundings twice a day at multiple locations all over the country. Our projects often do specialized soundings. These are weather balloons that carry small instrument packages aloft that give us vertical profiles of temperature, humidity, and wind. And so that helps us better understand the stability of the atmosphere and how likely clouds are to form. This is one of the things we look at is what our soundings tell us. In the images here, we see a balloon being prepared on the left, and on the right, the hardware that's used to actually acquire the data and process it. Another thing we look for when we're recognizing opportunities is we run numerical weather prediction models, or computer modeling, if you will. These are products specifically designed for our programs. This is a cross-section, a vertical cross-section across two ranges in Wyoming that have been involved in a program for a long period of time. What you see in brown is the vertical profile of the range itself. If you look closely, you'll see a 0.0 between the ranges. That's actually the temperature profile. And above that is a -5 that's in a magenta, and then there's a -10 that's in blue, and a -15 that's in the lighter blue, the cyan, above that. So the model's telling us our temperature profile, how that varies with height. We're also seeing some gray areas and some yellow and orange areas. The gray area are the cloud boundaries as predicted by the model. The yellow areas show the presence of liquid water, in this case, supercooled liquid water. It's all well below, well colder than -0 degrees, colder than -5 in that fact. And where it's the orangest above that second range is where the liquid water is the greatest. The third thing we need to know when we seed clouds is when we've identified the presence of liquid water, in this case, this model predicted liquid water. We're also very interested in what the cross barrier flow is. And so we see the wind superimposed at three different levels on the graphic as well. These types of models are run by WMI, but and other programs as well, that basically provide the forecaster, the person that's looking to initiate the seeding operations, some prediction of when onset might occur. We generally output this kind of a product in a 1 hour time step. So every forecast hour beyond initialization, we have one of these. So it gives our meteorologists a clue as to when to look for seeding conditions. They don't go off this alone, though. There's a lot more to go by. We also look at satellite imagery. And now with Go 16 and Go 17, we have a wonderful array of new tools available to us. One of our programmers has been able to process these data and provide them in real time to our forecasters. We have a visible infrared sandwich in the lower right there, the one that's mostly blue, that gives us a cloud top temperature. And in the one above that, we have day-night microphysics, which helps us differentiate between cloud type, water and ice. I grabbed this graphic because it's actually from a presentation that's going to be given this summer later at the World Meteorological Organization Weather Modification Conference in Pune, Italy. But I'd hope it actually does show that same zigzag pattern that Dr. Tessendorf showed from Snowy on this. This is a case from actually a program in California. However, the clarity of that, it doesn't stand out well enough that I can point it out readily. So what I've done instead is I've brought in a National Weather Service radar picture. I actually got 5 images here that I'm going to step through these. You see 2 dark colored blobs on the left-hand side. Those are the 2 mountain ranges through which you just saw the vertical cross section. This is not from the same day, but it gives you an idea of where the seeding might be occurring. And if you watch as I step through these 4 time steps, you'll see near the Colorado-Wyoming state line an actual zigzag pattern start to appear and go back and forth. So I'll go back again so we can see the initialization here. But we see that same kind of a pattern back and forth. Each pass of the aircraft is there. So I wanted to show you that's something else that our forecasters can look for to verify the presence of liquid water. Another thing that was also represented, it was a radiometer. I need to say a little bit about what a radiometer does and how it works. These are passive instruments. They don't transmit. What they do is they measure incoming radiation at specific wavelengths. One of those wavelengths is absorbed by water vapor in the atmosphere, and another is absorbed by liquid water in the atmosphere. And so when we see dips in the brightness temperatures at those wavelengths, we can say, oh, we have liquid water or we have water vapor. What I'm going to show you here is a graphic that shows an actual case. This is a radiometer that's pointed to look at 10 degrees above the horizon over the Wind River Range in west central Wyoming. And this is looking at liquid water content. And what we see here is the brightness temperature in the lower channel, and in the upper one, the same time period, the zenith integrated liquid water. So this is a case where we're clearly seeing liquid water form over the range. This is a real helpful cue to a meteorologist that's going to call for seeding operations, because even though they may look at a numerical model that says, hey, we have seeding conditions predicted at this time, if the radiometer shows the liquid water, that's an affirmation or a confirmation that the model is on track and that perhaps seeding should be started. Another tool that we use a lot are our eyes. Our eyes are really remarkable, especially during daylight. The picture in the middle here, we can see some clouds starting to form over a mountain range. It's getting lower and lower. I'm sure the meteorologist seeing something like this would go look immediately and see what the radiometer was showing. We also have webcams that are deployed. Some are by project, some are by other entities, and they just happen to be in locations where we can look at them and identify opportunities for seeding in that case too. I note here on the right that a webcam doesn't do you anything if it's pitch black. It doesn't do you any good if it's pitch black outside. But we found models now that are very good in low light situations, and they can even detect stars quite readily. And so if you need a yes or no, is it cloudy or not, that's very helpful. If you can see the stars or not. So the webcam actually has been a very useful tool for us. Once we see the conditions are right for cloud seeding and we start operations, we're going to target either with ground-based generators or with airborne seeding. Which we use depends, of course, on the program. Some are ground only, some are aircraft only. Some, like the Idaho Power Program, have both resources at their disposal. And in that case, you will turn on whichever can, you will turn on the generators if they can effectively target. That is, if the wind flow at the generator is cross barrier and that the supercooled liquid water is low enough that the seeding agent can reach it. The vertical distribution of seeding agent from ground-based facilities is limited to about 1 kilometer maximum. That's in the absence of convective currents, which in the winter we don't have much of. So the liquid water for ground-based generally has to be within a kilometer of the surface, 3,000 feet, if you will. And so that's a situation when you might start turning on ground-based generators. Those that are in the area that are showing supercooled liquid water, either by your model, by your observations, by your webcams. The other thing you can do is dispatch an aircraft. Aircraft are doubly helpful because not only do they tell you in situ, that is right in the cloud, whether the conditions are right, but they can also verify conditions for you. They can give you temperature, they can give you liquid water content, icing rate. The picture on the left, for those uninitiated, is a picture out the windshield of a King Air that shows the frozen cloud water droplets accumulating on the windshield. This is the sort of icing one would expect in supercooled cloud. It was mentioned previously that supercooled cloud flight is aircraft icing, and that's bad for aircraft. It's wonderful for cloud seeding. And so if we find the supercooled liquid water, we say, great, we can seed this. What we will typically do with an aircraft is climb just above the supercooled layer and drop those small ejectable flares that Ms. Golden referred to, the EJs. They're a 20-gram flare that burns up in 37 seconds, that just fall a short distance to seed the cloud below without staying in the cloud ice. So that's generally how we initiate operations when we see the conditions are right. If the aircraft gets up there and finds nothing, that means that our model was wrong or our judgment was wrong. Sometimes it'll be prudent to just have the aircraft wait around a short time to see if conditions actually develop. Other times they'll just return to base right away. If we've been seeding, we'll generally stop seeding when conditions are no longer favorable, and that means for an aircraft that's flying, they no longer are detecting liquid water, or perhaps the temperature is warmed to the point where seeding is no longer effective. Another thing that can happen is that you simply run out of seeding material. You've used up all the pyrotechnics on your aircraft, and you can't do anything more. So in that case, you can return to base also. With the ground-based generators, it's a little different. They can run for hours and hours and hours because the output is small, typically between 25 and 40 grams of silver iodide per hour. And so they can go even overnight, or sometimes longer than 24 consecutive hours if conditions last that long. But those are the situations when conditions are seeding is generally stopped. I think it's worthwhile to say a word or two about suspension. Programs always have suspension criteria, which, when satisfied, result in seeding ending, or if there's no seeding going on, you don't start. Typical criteria include the snow water equivalent, the SWE, the SWE of the snowpack within the target area, as how that compares to normal, and a percentage of normal. Available reservoir storage capacities may also come into play. There are a lot of other factors that can get looked at. Avalanche risk if it becomes extreme. Search and rescue efforts. For example, it's a standard operating procedure for WMI to suspend seeding operations in any area that search and rescue is ongoing because we don't want to be a hindrance. Even though the difference in snowfall might not be much, we don't want to come across that way. And another thing to note is the regulatory agencies. In this case here in Idaho, it would be the IDWR. The board would typically reserve the authority to simply tell the operator to cease and desist for whatever reason they might have. This is always the case where we've operated in the Western United States. Our client has always had that authority to tell us, even if they're just nervous about public perception or something, they can ask us to not seed, and we won't do that. This graphic you see on the right is an area, a season a few years ago in Wyoming, where we were monitoring a series of snowtells, 5 of them in one particular target area. When the average of the 5, which is the bright red line, crossed the 0.0, that meant our snowpack, our snow water equivalent, exceeded 140% of the regional of the median value for that time, and we went into the red zone, the pink zone there, and operations were suspended. Had the rainfall, had the snow water diminished over time, that is, it had melted off some, or had just not accumulated further and had gone back below the median, seeding could have resumed, but that did not happen there. So you can see the green area as where seeding operations were conducted. The orange area below that is where they're in suspension, and the seeding season is the combined total of all of those. So I think at that, just a note here about some other guidance that's available. Cloud seeding is really applied cloud physics. Dr. Tessendorf and anyone else that works in cloud physics will tell you that a lot of the discoveries in cloud physics were made because of cloud seeding research. The seeding procedures, protocols, and safeguards have been developed over decades. They're not something that is just out there that everybody's free to do what they want. There are some documents that are published by the American Society of Civil Engineers and its Environmental Water Resources Institute. These are updated on a regular basis, some of them every 10 years, others more often than that. We see a DOI down at the bottom for one of these. I'll just show you a picture here of the 2 documents that are available presently. If you go to that DOI, you can download or purchase hard copies of either one of these. These are out there for you. They cover basically every aspect of both winter, cold season and warm season programs, everything from design to evaluation. So these are guidelines that are adhered to by the responsible organizations, those recognized by the Weather Modification Association and others. And they're the foundational documents for how we do things as a cloud seeding company. So I'm going to stop there for the moment, and I'll come back later with Dr. Tessendorf to show a little bit more about water budgets.
Okay, board members, any questions? Okay. Next.
I believe Mr. Parkinson should be next.
Mr. Chairman, it will not let me share my screen. It's telling me that there's another participant sharing.
Oh, maybe I need to stop. Let me look how I do that.
All right.
I can't see, Sean, how I'm supposed to stop here. I don't see that menu. There it is.
Oh, there you go.
Yeah,
Let's
you
see
got it?
now. Stand by.
Jennifer cleared it out, Sean, so you should be good to go.
Okay. Let me see if this will work.
We're seeing it, Sean.
Okay, let me try to get it to full screen. Are you seeing the full screen or the presenter side?
Center side.
Let's,
Yeah, that'll work right
That's
there.
not bad, Sean.
that works there?
Mhm.
Well, yeah, you got the thumbnail slides on your left side, but that's not gonna bother us, I don't think. That works for you.
All right, we can, that a little better, a little bigger?
Yes.
All right. Well, thank you, Mr. Chairman. Thank you, everybody that's in attendance. And I am going to give an overview of the operational cloud seeding in southern Idaho. So I'll be building on some of the information that Ms. Golden, Ms. Tessendorf, and Mr. Bowe presented previously. I wanted to start off with operational cloud seeding in Idaho. Why? And Kayla touched on a little bit of this, but high elevation snowpack is a natural reservoir in the Snake River watershed. That high elevation snowpack is the last snow to melt, and that snow enhances river flows into and through the summer, a pretty critical time for our economy and a number of resources here in southern Idaho. Cloud seeding in Idaho increases that high elevation snowpack, and those benefits from that additional water include an improved aquatic ecosystem, irrigated agriculture, municipal and industrial needs, recreation, and then last but not least, hydropower. And that's really where that was what initiated Idaho Power's initial interest in cloud seeding back in the 90s. I'll start off with a little higher resolution view of where we're doing cloud seeding. So we've got the Central Mountains, and Kayla had this highlighted in her slides, but we've got the Payette, Boise, Wood River basins, and then the Upper Snake area. We've got the area that's above Palisades. We've got the Henry's Fork, and we actually seed some of the Mud Lake area also. And you'll notice here in the legend, we've got watersheds outlined, but then also target areas. I think it's important to note that we target the high elevations of these watersheds. We're not really targeting the whole basin itself, but these target areas that are the high elevation areas, that high elevation snowpack that's the last to melt. Before I go much further, though, I wanted to give an overview of some definitions so that I don't have to have all these words and make a bunch of slides later on really busy. And I don't want to be dazzling the audience with just a bunch of acronyms that everyone may not understand. So some of the weather models that we'll be using or that I'll reference or you'll see reference to, GFS, and NAM, those are publicly available models. The GFS is a global forecast system, so it basically forecasts weather across the globe. The NAM does forecasting in the North American area. And then WRF is a weather research and forecast model. It's widely used by a lot of researchers and operators. It's very customizable. Idaho Power has customized applications of WRF, and it's really, our use of it is downscaling results from the GFS and the NAM. So you'll see reference to WRF NAM and WRF GFS. Those are really just high resolution versions of the GFS and NAM solutions. And then WRF Weather Mod, as Tessendorf referred a little bit to this. It's a numerical model based on WRF that's capable of simulating cloud seeding. It can actually simulate the introduction of the additional ice nuclei so that we can see how cloud seeding plays out, and we can use that in a forecasting fashion so that we know where to seed. Some general definitions: National Weather Service, Natural Resource Conservation Service, River Forecast Center, CAF, you'll see that quite a bit. Those are thousands of acre feet of volume of water. SNOTEL is a network of instrumentation maintained by the NRCS. And one of the things that we're really interested in is SWE, snow water equivalent. That's how much water is on the ground at one of those SNOTEL sites. AGI, silver iodide, BIP and EJ, those are types of flares that Mr. Bowe referred to. And GGen, a ground generator. So that's a ground instrument that releases silver iodide. So the cloud seeding in the Snake Basins in water year 25, we've got a zoomed in map here, although it's a little bit smaller because it's crunched down, of the Central Mountains and the Upper Snake. And what these maps are showing are where the target areas are, but then also where the instrumentation is located. So we've got 39 generators targeting the Central Mountains. 24 of those are in the Payette. Some of those are shared with the Boise, and then 15 shared with the Boise and the Wood. What I mean by that is where we have instruments that are located on the watershed boundary, they can be used for either or, depending on the storm direction. Then these gray lines are flight track lines where the seeding aircraft can fly to release burn in place flares or release ejectable flares. In the Central Mountains, we have 2 aircraft that are based in Boise, which is down here underneath this legend. And those 2 aircraft can seed wherever the best seeding conditions present in any of these 3 basins. In the Upper Snake, we've got 25 of the remote generators in 1 aircraft that's based in Pocatello. And then in addition to the remote generators, there are 25 manual generators operated by Let It Snow. So here's Ms. Golden had some pictures of some of the equipment as well, but here's one of the Idaho Power remote generators, and then here's a manual generator that the Let It Snow program operates. One thing that I would note is that the difference in the remote versus the manual is because the remote can be placed in a location where it can be started and stopped remotely. It can be placed at high elevations above inversion levels so that the seeding opportunities over the course of a season are likely to be much greater. Some of the other capabilities that we have across the program, we have and operate a high performance computing system that can run high resolution WRF models. So these are the forecasting models that Mr. Bowe is referring to. We do run a WRF weather module so that we can use those models to predict where best seeding opportunities are likely to exist. We have a lot of the high resolution weather instrumentation that has been referred to, including cameras, strung out at a lot of these instrumentation sites throughout both the Central Mountain and the Upper Snake regions. There's a lot on this slide. I'm not going to cover all of it, but high level, I talked about the GFS and the NAM before. We use those larger scale models and we do downscaling at both the 5.4 and 1.8 kilometer. So this larger map shows where the 5.4 kilometer grid is, and then our high resolution grid at 1.8 covers from Central Oregon over into Central Wyoming, down into Nevada, some up into Central Idaho. So we have a very high resolution forecast of weather from this WRF model. And it's run 4 times a day for different durations, and both from the GFS and NAM, and then the WRF weather mods run twice a day in the winter months. From that, our operators can get a very good picture of what the future weather patterns are likely to be. They can prepare for cloud seeding operations. They can get aircraft notified. They can start looking at other observations to assess, are the forecasted storms likely to happen, when and where are likely best seeding opportunities to exist, and so on. Some of that weather instrumentation that we're using, we have high resolution or well instrumented sites throughout the Central Mountain and Upper Snake areas. We have weather instrumentation on our cloud seeding equipment. So this is the top of one of those seeding generators. We have a number of radiometers in both the Central Mountains and Upper Snake. We have high resolution precipitation gauges, and we also launch weather balloons so that we can get the upper air soundings that complement what we get from the radiometers. So a summary of operations from 2025, Central Mountains and Upper Snake. So this column here are the hours of ground generator, silver iodide ground generator operations through the course of the year. This column are aircraft flight hours, the total number of BIP and EJ flares that were used in the Central Mountain and Upper Snake areas, and then the total silver iodide released. So 2025 was not a phenomenal year. You can see that both the ground generator use was less in 2025 than average. The aircraft hours was lower. The flare use was lower, and the silver iodide released was lower than average. To put these silver mass quantities into some context, and you'll see a little bit more from some of the future presenters on the mass here, but on average in the Central Mountains, we've released 63 kilograms of silver iodide, and in the Upper Snake, 37 kilograms of silver iodide. That totals 100 kilograms of silver iodide released each year. The total target area in the Central Mountain and the Upper Snake area is about 14,000 square miles. If 100% of that silver iodide that's released falls within the target area, which is an unrealistic assumption, that equates to less than a tablespoon of silver iodide per square mile per year being released. So just trying to put the quantity into context for the areas that we are seeding. Moving forward, looking at an approach to evaluating how much benefit we get out of our operations, we've used an approach called target control. We look at control sites, and we are specifically looking at precipitation and control sites. So these are precipitation gauges. This is the Oregon-Idaho border here. So upwind of where our weather typically comes from. The red ones are control sites. The blue ones are target sites. So these are precipitation gauges that fall within areas that we intend to target. We look for periods that we have data from the control and the target that predate when we seed. We develop a regression of between the control and the target precipitation in those areas. And then we can use that regression and look at periods when we have seeded. So this graph is showing for the Payette Basin. We started seeding in 2003. So the preceding line is using data from 82 to 02. And then we started seeding in 03. And so we use that regression formula and we look at what we would have predicted and then what we observed, and the difference between here is the benefit. So when we use this sort of a regression model in each of the areas that we seed, we have an average benefit for the years that we've been seeded. In each of the sub areas that we look at cumulatively, in the Central Mountains, we've seen about a 10% increase in precipitation in that November 1 to April 1 seeding period. In the Upper Snake, we've seen in the Henry's Fork about a 5.5% increase, and then in the area above Palisades or the Upper Snake, we see about a 9% increase. Wanted to share some results from some other areas that had a long enough seeding record where folks had gone in and looked at what the seeding increases were in those other watersheds. So here's some basins in the Sierra Nevada mountains in California. Bernie Sullivan looked at stream flow increases, so this is different than ours, and we'd expect there to be some losses from precipitation to runoff. And he found a 5.1% increase in the Kings River Basin in a 2007 review, a 6.4% increase in 2008. The Vail Basin and the Gore Mountain Range in Colorado, he found a 6.3 to 28% increase in stream flow runoff. Super and Heimbach found about a 15% increase in snow water equivalent in the Bridger Range in Montana. The Snowy Mountains, they found a 14% increase in precipitation. I'm just showing these papers and the results of these evaluations to reflect that what we're finding in the Central Mountains and the Upper Snake fall within the realm of what other investigators have found in looking at precipitation and stream flow increases from other cloud seeding programs. I'd note that these programs all use just ground seeding and haven't used aircraft seeding. If we take those precipitation increases and apply those to a hydrologic model, and that hydrologic model uses a number of inputs, including temperature and precipitation. So we're modifying the precipitation that we put into that model. In a with and without scenario, we see that the difference in the Payette is about 200,000 acre feet per year. The Boise about 240,000 acre feet per year. In the Wood about 100,000 acre feet per year. And in the Upper Snake about 613,000 acre feet per year. In total, about 1.15 million acre feet per year of additional natural flow. So this is unregulated runoff between the Central Mountains and the Upper Snake areas. Mr. Bowe touched on programs using suspension criteria. We have suspension criteria that we use to guide operations in both the Central Mountains and the Upper Snake. We look at snow water equivalent from the NRCS SNOTEL. So this is a graph that our operators have available to look at for each of the areas that we seed. The red line indicates when we would suspend. The black line indicates the observed SWE in each of those areas. If this black line exceeds the red line, we suspend operations until it drops back down. We also watch for flood potential. We watch the River Forecast Center, and we have a flood index that we watch. We also monitor the National Weather Service for flood warnings, rain on snow events, and other extreme conditions that could cause concern. The avalanche conditions that Mr. Bowe referred to. We also monitor severe weather, which could include locally heavy precipitation, strong or damaging winds, hail, lightning, etc., and then other special circumstances that might come up. That's all I had prepared to share on the operations of the Snake River cloud seeding efforts. And I will stop sharing.
Okay, committee members, any questions for Mr. Parkinson? Okay.
Next, Mr. Chairman, we'll have a couple of presentations on environmental considerations of cloud seeding. And we have, looks like Ross Edwards, senior scientist with University of Wisconsin, and Pat Golden, principal biologist at Heritage Environmental Consultants.
Okay, welcome.
Thank you all. This is Patrick Golden. I want to apologize. I got called into the field, so I'm sitting here in my truck, so I don't want to share my face. And we're going to have Ross do most of the presentation because I'm tethered to my phone, but thanks for having us.
Okay, thank you for taking the time to be here.
Thank you. I'll take it away. Yeah, thanks everyone. So we're just going to present some information on environmental considerations, cloud seeding. Primarily, we're going to talk about silver iodide. So Pat and I have been involved in this kind of work for quite a while now. I guess originally with myself, I was a professor at the Desert Research Institute, and we were helping out with Idaho Power, looking at background of silver as well as targeting. And then later on, some work in the Wyoming, the Medicine Bow Range and Wind River Range. So silver in the environment. Sorry about this, I've just lost my slide. So silver is a naturally occurring element, obviously. It's present in soil, sediments, etc. But it's in very, very low amounts. So in the sediments and soil, the averages are about 0.1 to up to 1 parts per million. And it's very difficult to measure. I want to just state that. So some of the considerations that you need to have when sampling for silver is to be very, very clean to prevent contamination. So in this, on the right side, we have some of the silver concentrations varying from baseline snowpack. These are some of the measurements that we've made at around 1 to 2 parts per trillion. And then in fresh unpolluted streams, 1 to 30 parts per trillion. And a part per trillion is hard to wrap your head around, I would say, but the comparison is one drop of water in 20 Olympic-sized pools would be about 1 parts per trillion, or 20 parts per trillion would be 1 drop in 1 pool. So just to consider how small that is. But again, in the Earth's crust, it's around anywhere from 90 parts per billion up to anywhere up to like 800 parts per billion in soil and stream sediments. It can vary quite a bit from place to place. That's one thing I want to say. But it's pretty low if you think about it. It's unexpected. It's almost unexpected how low it is in the background. And so there's lots of different forms of silver, and this is the other thing I just want to point out. So there are lots of studies now about silver and with respects to toxicity to aquatic organisms, etc. But silver has many different forms. There's just a few of the forms of silver. So we have silver, metallic silver, silver nitrate, silver chloride, silver iodide that we're concerned about with weather modification, and then silver sulfide at the bottom. And I've just arranged these in their basically in their solubility, if you will. At the top we have silver nitrate, which is kind of what you'd expect to find in the burn unit at the hospital. So this is completely dissociates into silver ions and nitrate ions. And then as we go down, we're progressively getting less soluble or less available, I would say. And right at the bottom, we have silver sulfide. And silver sulfide is essentially what all forms of silver will end up as, typically, right, in the environment. If you release whether it's silver nitride or silver iodide, eventually it will encounter some sulfide somewhere, and it will become silver sulfide. And that's pretty much it. And silver sulfide is extremely non-toxic, and it's just that's just a stable form of silver that everything winds up as. And so the toxicity of silver is we're primarily concerned about the silver ion Ag+. So the thing about the silver ion is that it's unstable in most water bodies or in most reservoirs in the Earth system. There are no reported fish deaths or deaths of any form at least that I know of from silver. Part of the reason that we're even concerned about silver at all is due to silver being used at scale in the urban environment, our modern environment. It shows up now in keyboards as very, very small nanoparticles of silver, to everything from toothpaste to packaging, electronics. And so it's been increasing in sewage. And so there's been some concern about that stream of silver getting into water bodies, or sewage sludge being used on land, spread on land, and the impact on the environment. So there is a large amount of silver in the urban environment, but silver iodide in particular is fairly it's considered non-soluble, although there is some production of silver iodide associated with it. The World Health Organization, EPA, most state government water quality standards have set 100 ppb as a secondary guideline, I think, for total silver in the water body. And the thing to remember, though, about silver is that whilst these thresholds and regulations are set, what we're concerned about is not so much the concentration of silver in water, but the activity of water. And the activity is determined by the water chemistry, pH, ionic strength, other species. So you can have quite a bit of silver, but if in a water body, but if the chemistry of the water body, like the water hardness is high, or there's high amounts of sulfate, etc., the actual active concentration of silver can still be very, very low. Okay, and so the toxicity levels. The other thing is, it's for silver iodide too. Because of its solubility, even if you put a large amount of silver iodide in some water body, the saturation concentration, the highest concentration it can reach, would still be soluble, is a little bit under a part per billion, which is below the threshold for toxicity anyway. The toxic level of silver Ag plus in rats is about 95 parts per billion. Germinating plants is 750 parts per billion. So, et cetera, et cetera. So it's much higher than what you could reasonably reach in a normal environment. And in terms of accumulation, silver primarily accumulates in sediments, soils and stream beds. The particles of silver iodide they're used in cloud seeding are not stable as a particle themselves in water, and will attach to other bigger particles. And so it's not that mobile in the sense that it's not like freely floating around the place in water bodies. It will transport as part of attached to clay and other sediments. And so when we've been sampling in the snowpack and as part of some of these studies, it's very difficult to even find any silver. Okay, so that's something. And then rivers and streams that we've sampled, I'll present that in a minute. We've always found very, very low levels. So I mean, it's the actual amount from cloud seeding is about an order of magnitude lower than what we would, or orders of magnitude lower than we'd find naturally in soil, especially in Idaho, where there has been a lot of silver mining and silver-rich ores around. And I just wanted to note, though, that when you are sampling for silver in these snowpacks, you have to be very, very, very careful about contamination. And there is a little bit of data in the literature, which I'm pretty convinced is contamination. If you really go, we have to wear like clean suits, and we prepare our bottles in ultra trace clean conditions and acid wash everything. So this is some data from the Wyoming weather modification pilot program. And so we did some background water sampling prior to the study. And so we're finding anywhere from less than 1 to 10 parts per trillion in the river system. And you can see as we go through from starting at 2005 to 2014, the red bars are the silver. There's no change in the rivers, and we wouldn't, to be honest, wouldn't expect anything to change. And so this is natural silver just eroding out of the landscape. And this is a background snow profiling that we did. Again, this is Battle Mountain in Wyoming. And you can see we did this very high density sampling. I think that's me there in the snow pit with these tubes in the snowpack. And then on the right here, you can see we have the density of the snowpack, but then also the silver. And this is the background. In the background, you can see it goes from anywhere from 0.3 parts per trillion, so that's 300 parts per quadrillion, up to around maybe 4 to 6 parts per trillion. And so the thing we have to account for in the snowpack is that you do find dust layers in the snowpack from atmospheric dust that's blown in, and that dust does contain silver, natural silver. And so just because you find a little bit of silver in a snowpack doesn't mean it's from cloud seeding. So we have to carefully try deconvolve the cloud seeded silver from natural silver. But so in this case, it's natural silver. But anywhere from less than parts per trillion to something like 6 parts per trillion. Okay, and so this is just showing inputs of silver from cloud seeding into Central Mountains, Idaho, and Upper Snake. This is what Sean was showing just previously. This is just some calculations that I made. So based on the total amount of silver iodide of 100 kilograms released per year, target area is about 14,000 square miles. And so if we assume that, this is not realistic, but if we assume that the silver iodide is evenly dispersed in the target areas and 100% of it lands there, and it lands on the soil, like a piece of soil that's 40 inches in square and about 4 inches deep, and it stays there forevermore and doesn't move, then our estimate is that it would take about 10,000 years of cloud seeding to double the amount of silver in that piece of soil. So in this calculation, we calculate about 1.27 micrograms of silver per, this 40-inch unit, which is about a meter squared. And then you also have dust coming in, and so the dust, and this is a pretty conservative estimate as well, atmospheric dust that's blowing in with silver about 0.1 to 1 micrograms of silver per meter squared per year. So, and I don't think Idaho Power is interested in cloud seeding for 10,000 years. So, and then just bioaccumulation, which is the buildup of a substance as it moves up the food chain. The most notable cases of bioaccumulation would be mercury, probably. In this case, the toxicity depends on the concentration of the active free silver ion in the water again. But there's no real evidence of bioaccumulation, at least in the natural environment. Up the food chain, there can be some accumulation of silver in algae, but it can be bound to the organic material. And so it's a question of, again, the state of the silver ion, how bioavailable is it? Even in fish, it can be ingested and passed through as waste without showing significant bioaccumulation. But just to hark back to one of my earlier statements, ultimately silver ion will become silver sulfide. Once it becomes silver sulfide, it's pretty irreversible, an irreversible transformation. And so most of the ore bodies that we find with silver are sulfide minerals. The permitting, so there is permitting is required generally for cloud seeding, and this is related to needs for environmental studies, etc. But so this is more Pat's area, but so many high elevation lands in the Western United States that are being targeted for winter orographic cloud seeding projects are often managed by federal agencies, such as the USFS and BLM. And so there may be some requirements for equipment permits, the special use permits for some of the federal lands, temporary use permits, which may or may not trigger environmental reviews. So not all of these, I guess, usage require environmental, mandate environmental review. But there is the National Environmental Policy Act and the California Environmental Quality Act, and also Endangered Species Act, which require proper environmental reviews. But if the activity is conducted on private or state lands, doesn't always trigger the NEPA. And then there's reporting of ground aerial operations which have to be reported to NOAA. And so NOAA has a library which has all of these reports dating back, I think, into the 1980s. So just to summarize, the total silver concentration seeding orders of magnitude lower than what we expect to find in just average soil. So it's hard to, if the seeding is conducted as, typically these programs are conducted, it's hard to imagine, it's impossible to build up levels of silver that are really exceeding the background. Silver iodide's relatively non-toxic, it's fairly stable, it's practically insoluble, doesn't really dissociate into water, it's not essentially becoming toxic, and eventually it will be converted to silver sulfide. Although silver ions from soluble silver salts have been shown to be toxic to aquatic species in the laboratory setting, it's not really the case in the environment, just because of the nature of natural water and ground. It's not like again, like the burn unit where you're dumping a bunch of silver nitrate on to kill microbes. I've just been talking about the silver aspects of it, but the extra area effects obviously are more about, you know, the water and water budget suspension criteria. So just some references and any questions?
Okay, committee members, questions? Okay, I think we're good. Can move on.
Next, it looks like we'll have Dr. Tessendorf and Mr. Bowe back for a summary and recap.
Yes, we're going to have Mr. Bowe start us off on this last part, especially to talk about those extra area effects that that Ross just mentioned. Bruce, are you available?
Yes, we're getting there.
Okay.
Let's see here. We got a chair. That's that one. Then I need to start my PowerPoint, and that would be this one. Okay. Are we back where we left off?
We don't see your slides yet.
You do not? Okay. Thank you. We'll go back and try again here. We'll try share. Screen 2. Share.
That's looking better.
Okay. Yay. Let's try it here. Apparently I have to do share twice, so sorry about that. First thing is, it's important to remember that cloud seeding makes an incremental increase in natural precipitation. The net precipitation remains well within the bounds of natural variability. What I'm going to do next is look at a few slides that'll help us better understand the natural water budget and the impacts of cloud seeding. This is the obligatory diagram of the hydrologic cycle that gets shown in any talk about hydrology and how water moves around in the environment. I've put the question on there, does cloud seeding just redistribute precipitation? Because in all of my years of working in this field, is probably the biggest question I get is, if we make it rain more in one area, does that mean somebody else gets shorted? And it's a logical question. It stands to reason. What we see here is evaporation and transpiration lead to condensation in clouds, which then produce precipitation, which result in groundwater recharge and surface runoff. And the surface runoff then can contribute to the recharge of surface reservoirs, rivers and lakes and streams and that sort of thing. So I think we're all very familiar with that. But let's look at it a different way. Before a cloud forms, everything we have in the sky in terms of moisture is water vapor. It's not visible. And so we can't see it, but it's up there. When a cloud does form, perhaps, and this is being very generous, perhaps 20% of the moisture in the atmosphere where the cloud forms would actually turn into cloud and be removed or become visible from the atmosphere. And so with that, we now have a cloud that we can see, but at the same time, 80% of the moisture that was there to begin with is still invisible. And to illustrate that, I've created this more complete version of the hydrologic cycle that I like, because you can't see the water vapor and it's always omitted from it's indirectly covered by the transpiration and evaporation areas, but it doesn't show up in any visible way in the diagram. So I like to put this in to remind people that when a cloud forms, it's not like all the water in the atmosphere goes into the cloud and there's none anywhere else. It's very much different than that. It's probably far less than 20% of what's in the atmosphere at any location that ends up in a cloud. But let's suppose that it's 20% and that the cloud is 30% efficient. That is 30% of its condensate it can convert into precipitation. This is a pretty effective cloud. When we do that, 30% of the 20% is 6%. So that would be the natural precipitation we'd get out of the cloud without any cloud seeding. It'd be 6% of the total that was in the atmosphere at that localized area. If we seed the cloud and the cloud is 15%, we're 15% effective at increasing the precipitation from seeding, then we end up with this little tiny yellow sliver, which is less than 1% of the total in the atmosphere. But that'd be 15% more precipitation than natural. So you can see we can get a lot more precipitation out. I mean, that 15% is very significant, but we're really not impacting the total atmospheric water budget very much. It's a small amount, and this 20% is a generous amount. Probably less than that when you look at the actual environment around the cloud and all that. We also have to remember that seeding occurs only when the conditions are right, which is a small fraction of the time. We also need to note that the atmosphere recharges very quickly. As soon as precipitation falls from a cloud, transpiration of that precipitation on the ground by plants and evaporation from the wet surface automatically returns a significant fraction of that moisture to the air. In the wintertime, sublimation is very active, and in fact, snow, particularly on fresh snowfall, sublimation will return a fair amount to the atmosphere as well. And so there, the net impact of cloud seeding is a small fraction of what goes on. As we go a little bit farther into that, you also think about if you're downwind of an area and you're concerned about cloud seeding upwind of the area, the moisture that's moving down, or the air that's moving downwind to you from the upwind area, is going to contain more moisture if in fact they have had more precipitation. And so that's another plus. I'm not going to get into the weeds on this, but I am aware of a number of evaluations that have been done of cloud seeding that actually show a benefit in terms of precipitation effects downwind of the actual target area. The last slide I'd like to show here is, well, not quite the last, but nearly the last, is a graphic I made a few years ago because I thought it useful to see, to compare time scales in recharge. I noticed that Dr. Edwards, in one of his last slides of silver concentrations, used a logarithmic scale in the vertical axis to show the amount of silver present in snow. In this case, I'm using a logarithmic scale on the horizontal axis with time in weeks. And I've put some additional dashed lines on there to help you understand what the time frames are. The first vertical dashed green line is for 1 hour. The second one is 1 day. The 1 week line is a solid white line because it is a week. We go a month is the third dashed line, and then a year is the fourth. And what you should take away from this is groundwater resources recharge sometimes takes a very, very long time. It can actually take many, many years, even millennia, depending on the nature of the strata above an aquifer to recharge groundwater. Surface reservoirs are somewhat faster. Heavy precipitation events can fill reservoirs relatively quickly. I've seen reservoirs with spring runoff fill in a matter of a week or two in the western United States. Often it takes longer than that. In drier, more typical conditions, it could take a long time for that. But atmospheric water, on the other hand, comes in with the wind. And depending on what that wind direction is, it can be very, very rapid. Within an hour, you can have more moisture in. If you look at a thunderstorm when it produces or puts water on the ground, how quickly that returns to the air. It's very, very quick. And so the idea is for cloud seeding is get the water out of the atmosphere on the ground where we can use it and a lot of it, when we get it to the ground, goes back up relatively quickly. A couple of things I think that are also helpful for us to remember about what cloud seeding can do. Realistically, we can increase precipitation incrementally, that is fractionally, over and above what nature can give us. Therefore getting more water to the surface where we can use it for all of the purposes that Dr. Parkinson mentioned in one of his first slides. Use of the technology can make no claims on any water thus produced, that is, at least in the Western United States. Water from cloud seeding is considered part of the natural water supply, and it's treated accordingly under Western water law. So people that do cloud seeding can't claim additional water, and we don't, and it just become part of the system. Water managers in the Western U.S. are using it increasingly to help make systems whole and to add supply to over-appropriated systems. Related to that, I'll mention very briefly here that the heavily populated and water-scarce lower basin states in the Colorado River, that's California, Nevada, and Arizona, have for well over a decade now been putting money into cloud seeding programs in upper basin states, Colorado, Wyoming, and Utah, because they are hopeful that the additional water thus generated will get into the Colorado River basin and make it down to them. Because water for them is way more valuable than it is up in our part of the world, and so these are established cases where large water entities, water managers are making decisions based on this that are putting millions into these other programs each year. It's also important to note what cloud seeding cannot do. This is winter or summertime. Cloud seeding will not break a drought. It may help you recover faster from a drought, but it's not going to end the drought. And it's very important that expectations be tempered when programs are started because of acute water shortages. Cloud seeding cannot create clouds. It can also not move clouds, and it can't change cloudiness, winds, or temperatures. We have sometimes hear this from public that don't have good science backgrounds. They don't understand this. And then the last thing is that cloud seeding can't ensure that it won't rain or snow on your wedding, party, or rally or whatever. And I know this sounds really silly, but every year we get multiple requests from people wanting to know what it would cost to make it not rain on their wedding day or whatever. And that's just not something we do. A few years ago, during one of the Olympics, China claimed to suppress rainfall so it wouldn't precipitate on the summer games. And I'm not sure how you could do that reasonably, but they claimed that they did it. So that's another thing I don't think cloud seeding can do, but the Chinese say it can. So anyway, with that, I will thank you for your attention and turn the microphone on the stage back to Dr. Tessendorf.
Thanks, Bruce. Can you stop sharing your screen?
I'm getting there.
Okay.
It takes me a minute here because there we are. My screen shrunk up, so I need to unshare. I see the share arrow. Not sure how to undo it. Did that stop?
Yes.
I don't
believe
know.
it did, yes.
Okay.
Okay. Thank you, Mr. Chairman and board. I am going to wrap us up. Let me get this into slideshow mode. Okay, and do you see the full slide?
Yes.
Can't tell which screen has the slideshow. Okay. All right, so I just want to wrap up a quick summary of some of those common questions that we just heard some answers to, as well as address one more, and then talk about where the research and the science is currently at and how we're supporting the state of Idaho with that research. So just to summarize, as Mr. Bowe just described, in this field, we get a lot of questions. Every time I talk about cloud seeding, I usually get the same questions because they're very common. And so one of those is, does cloud seeding with silver iodide impact the environment? And we heard from Dr. Edwards that, silver is naturally occurring in the water and soil, and the amount from cloud seeding is actually quite hard to detect against those background levels of silver. And also because it is insoluble in the silver iodide form, it does not pose a health hazard. As we just heard from Mr. Bowe, discussing extra area effects, we often get asked very candidly, are we robbing Peter to pay Paul? And this question, is rooted in that physics conservation of mass principle. But when you think about what mass we're really conserving in the atmosphere, it's really that water vapor, which is that total pie that Mr. Bowe showed. And so, with that understanding, the impact of cloud seeding on that total amount of water vapor in the atmosphere is very small. And the atmosphere does recharge the water vapor over time as well. So that pie was a snapshot in time, but we always have moisture, water vapor moving through the atmosphere. So it's thought to be very small and is often also hard to detect. Another topic is, could cloud seeding lead to hazards like flooding or avalanches or other concerns like that? And as we heard from Dr. Parkinson and Mr. Bowe earlier too, these programs that conduct operational cloud seeding follow suspension criteria that are specifically designed to not conduct cloud seeding in certain situations in order to mitigate real or perceived hazards like cloud seeding, relation to flooding and avalanches. But I also want to point out, as I described earlier, the impact of cloud seeding on precipitation is still relatively small compared to the natural variability of precipitation. That amount of change in precipitation from cloud seeding cannot take a storm that would not have produced a flood and suddenly make it flood. That's just not the amount of available additional water that we're able to bring down out of the cloud from cloud seeding. So that's also not a likely concern. So the other topic I want to briefly discuss is related to contrails. I've observed there's often confusion about contrails that are observed in the sky and cloud seeding. And so I want to talk a little bit about contrails and what they are, but first I want to review how clouds form. I've worked a lot in an educational setting where I like to do an experiment where we create a cloud in a bottle. And it's a nice experiment because you put the different ingredients for a cloud to form together. And if you're missing one of those ingredients, you don't get that cloud to form. So there's 3 ingredients. I'm going to cut to the chase. If we had time, I'd love to do the experiment with everybody because it's fun to get your hands involved in some experimentation. But the 3 ingredients are cooling. As I mentioned earlier, one way that clouds form over the mountains is because the air flows up and over the mountains, and as air goes up into the colder parts of the atmosphere and the air expands, it cools. That cooling allows condensation to form. But then you need moisture. That moisture is what's going to condense from the water vapor into the liquid cloud droplets. But the third ingredient that not everybody understands right away is that we also need aerosol particles for that water vapor to condense on. Water vapor will not condense from gas phase of water vapor to liquid phase without a particle. And so this is where, we talked about how that relates to cloud formation and cloud seeding, but this also relates to contrails. So human activities can create clouds under special atmospheric conditions. For example, when the atmosphere is cold and humid and we inject some additional aerosol particles, so that's getting us, we already have the atmosphere set up for ingredient 1 and 2, and then we add some aerosol particles. Another way we can create clouds is by adding some additional moisture. If we have a cold environment, but we add some additional moisture to the air as well. I'm going to give you a quick example that many people probably can relate to on a cold, humid day. If you ever breathe out through your mouth, you actually create a small cloud because you're adding some additional moisture to the air. But so in the examples that I'm showing on this slide, we have contrails that form when aircraft are flying up at high altitudes, so it's cold up there. If the air is near saturation, so it's humid but not quite enough to produce a cloud, and then the aircraft exhaust provides both water vapor and particles from the exhaust that can then create the cloud up there. We see this down closer to the ground on cold, humid days as well. You've seen these contrails probably from a car. When a car's engine is just starting on a cold, humid day, before the engine heats up, you'll see an actual cloud. It's not smoke coming from the exhaust pipe. It's just the cloud that's forming because the exhaust of the car is doing the same thing, producing some additional water vapor and particles into the atmosphere under those certain conditions. And another place that you might see it again on a colder, more humid day is from exhaust pipes, exhaust towers, cooling towers in industrial plants. Those exhaust clouds billow above those towers. You don't see those every day because the atmospheric conditions that lead to them have to be just right. One thing that you will see is that contrails, sometimes they last longer than others, and when they last longer, the winds can spread them out. And that's again due to the atmospheric conditions. If the atmospheric conditions where the aircraft are flying allow that cloud to linger for longer, it will. If it evaporates right away because the air up there is really dry and that initial burst of moisture and particles created a cloud, but then it evaporates right away, they won't last very long. But so on the lower left, I have a photograph of what you can sometimes see from the aircraft. And I'm going to just add a quick image that I got on my phone 2 days ago. It was afternoon, late afternoon. This is southwestern Idaho. You'll probably recognize the state line here. This was a snapshot of all the aircraft flying in the air on FlightAware. And so you can see on a day where the atmospheric conditions are conducive to a cloud to form at those upper layers, when you get those additional ingredients of moisture and particles from the exhaust, you'll get zigzaggy, crisscrossy patterns across the sky. But on days when it's more dry up there, you won't get those at all. So cloud seeding is not the same as contrails, but they are both mechanisms where particles from human activities are being put into the atmosphere, enabling cloud processes to be affected. But contrails, of course, are not intentionally trying to modify the atmosphere, whereas with cloud seeding, we are trying to enhance the precipitation in the cloud. So the last thing that I'm just going to wrap up with is getting back to this illustration of the atmosphere and the processes that are at play. We are currently trying to, answer questions that the state of Idaho has regarding the impacts of cloud seeding. And there's various components to this to comprehensively address these questions that we've been building computer models and improving computer models to address. The first component is we have to be able to understand and represent the natural cloud systems and weather systems. This is important to have models that represent these so that we can forecast the cloud seeding opportunities, like you heard about from Dr. Parkinson and the Idaho Power Program. But we also use these models then to drive simulations of cloud seeding to simulate the seeding processes to look at the impacts on precipitation and stream flow. So that's parts B and C here. Whereas for part B, we've developed a model which is called WRF Weather Mod, as you heard about from prior presenters. This simulates those processes that were on the conceptual diagram I shared at the beginning of the presentations. That simulates the release of the silver iodide as well as the growth into snow and the fallout of snow. But then we're also developing models that look at the hydrological impacts because we want to understand the stream flow impacts. And so those hydrology models, the one that we've been developing and working with is called WRF Hydro. WRF Hydro can be driven by the output of WRF Weather Mod, and then it simulates all the hydrological processes that result in stream flow, but as well as the evapotranspiration, the recharge, things like that were in the water cycle diagram that Mr. Bowe just presented. This is not specific just to Idaho either. We are working in other Western states. There's lots of Western states interested in cloud seeding to augment water resources, as Mr. Bowe presented on the slide of all of the Western states that are doing cloud seeding. Some of them are looking into the feasibility of cloud seeding in their states. So we've been working to study the feasibility of cloud seeding in those areas. We are also working in your neighboring states of Utah. Utah is very much interested in this. They've been cloud seeding for a long time, and they recently have had the opportunity to put some resources into the research to better understand and quantify the impacts of cloud seeding. This is especially important for them because they are having severe stress on the Great Salt Lake. And so water resources issues are really driving the need to do this type of research and better understand how and if cloud seeding is an opportunity for water resource management and mitigation. And then I also just want to credit, Wyoming. The state of Wyoming has been doing cloud seeding for a while now, but they really kind of led the way back in the early 2000s in bringing back scientific research to study this topic, and really brought to bear all of these different resources in the modern era of computer modeling and the modern era of observational technologies, and really brought them together to do a modern day statistical experiment to look at cloud seeding, and have been supporting the research for that as well. So with that, I think that's most of my remarks that I had. So I will turn it back over to you, Mr. Chairman.
Okay, thank you very much. Okay, that completes all of our presentations.
Yes, it does.
We've been at this for about 2 hours. I would suggest maybe we take a 10-minute break and then come back to the next item on the agenda, which will be public comment in about 10. That's okay with everybody? Okay, we're in recess for 10 minutes. Yeah, hey, Leslie reminded me, if you're here and you intend to give public comment, please make sure you're subbed out when you check the box that says you would like to give comments so that we don't leave anybody out.
These are, the AIG projects are mainly water efficient. Generating slurry immediately or
Like this good
direct connection.
It's just
Well,
all.
So,
But I mean, like you see that. Get activities going on. Like Larry, mountain tunnels. So anyway, I can try to do splits, several over the year. Anyway, we can kind of, we can frame it, we can shape it.
Wait till you see what's coming.
Like you could get really good. A lot of it.
True. It sounds like the groundwater.
I like the idea of flying a stripe here, not with space and reflecting down light. That I don't think is a good idea. We're talking about like.
So not a plan of reflex over.
No, they just announced they closed that route. Yeah, for him.
Yeah, it's also like you shoot targets. It's gonna be lasers.
We need energy that fast. So yeah.
I was just seeing him all the time.
They'll probably just call like those.
Well, it might be a topical thing. Feature about cloud seeding.
Yeah. Well, that was good. College class, good college class.
I mean, like an hour and a half. Yeah. I'm flying, I board my flight at 5. In and out. Two days. Ranches, small ones, but there's a lot. I should say you're from right. What do you guys do here? I was talking to a real estate developer in Liberty Hill. Texas. All developers that built water. So what would you do?
Will your state allow it?
We do that. One of the Texas.
Potentially.
I started my first. I didn't know that was happening in Idaho.
Yeah. In Utah, since the 70s. I mean, like the western states.
It looks like Wendy's gonna go down.
On like directional, having an impact.
We didn't know it. We didn't know it really worked until like 2017.
Yeah.
So it's literally all.
We've got road part of the initial catchment from the hospital.
Oh, is that gonna be gone by junior part?
2 years.
But I don't see it.
No, so you have to go clear.
Yes. So the whole like That's why you want to be running, especially west, but even east, all their water is just like thermal. So, we're seeing drought.
On that one slide, they were saying it increased the vapor that came down.
Just follow me through this. But.
At least there's a treatment.
Yeah.
Back. Make a note of that. Okay.
But anyway, and then a hot side. So then the other side.
They were interesting. Yeah, except he was the hardest guy to follow. Mike was bad in his accent. Yeah.
They had a technical workshop. He said that one of the issues that we're kind of running into is something less expensive and getting the right spot, the right point. So the relationship between 1904 and the USGS storage. Hundreds of thousands of dollars. Yeah, give the people that.
Before we hit the wall on our face and study proposal. That's huge.
With crosscuts. Yeah, okay. They came in handy for that.
Thanks for doing that live test for us.
You can watch us here.
A lot harder than physics just because it wasn't.
Okay.
We live. So, what's the state? That would be something to watch when it goes down. Yeah, so I take a video.
USGS.
Their president.
That's
World War II.
Yes, Mike.
See like the hair and the sweat.
USGS gets suspicious of what
The artist who did these, hairs on his arm.
All these materials.
And then they had the voice in the background. Sorry, what happened there?
So it all relates to
The guy that did those.
So we can measure how deep it is.
They know.
They don't say we reliably now know.
He wants to get the-
And they just did a shoot update on Palisades. Because that's the system. Money
turns right about change of the presidential administration with some budget. Topic of the day.
We had a morning meeting with the Bureau of Reclamation. They're like paralyzed almost. Their staff. They lost the highest performer.
Talk to Jamie. No, I'm just a small piece of it.
Oh, yeah, okay, perfect.
I think they just do.
Yeah, I'm good with it, actually.
Fires, so.
And
And then someone else. I started when. Oh.
All right. Okay, we're going to reconvene the committee meeting. We're going, the next item on the agenda is public comment. Before we get to that, I want to recognize we have several legislators with us here today. We appreciate them taking time from their busy schedules to attend our meeting and get caught up with the water board's efforts around cloud seeding. I do need to note that this whole committee meeting is being live streamed. I understand a couple of people have had some difficulty getting onto the YouTube channel. I don't know what that might be, but it will be available on the IDWR website. And you'll be able to go back and you can tell your friends that they can go there and view the meeting. You can go back and review it at your leisure if you so choose. We'll now move into public comment. I'm also going to say that for those who were not able to be here in person who wish to give public comment, we will accept written comment. We'd like to get those comments in a timely fashion in the next few days, if that would be at all possible. But we want, if somebody has something that they would like to share with this committee and the water board, we would like them to have that opportunity. So you can do that either here today in person or with written comments. For those who are going to testify, we need to know your name and if you represent someone or somebody, that you tell us what your affiliation is. And with that, I've got a few people who have signed up and indicate they want comment. First, we have Ron Abranovich. Ron?
Yes.
You get to be our first test drive here to see if this is going to work. Looks like our camera's working. Tell us who you are and what's down your mind.
Okay, thanks, Mr. Chairman. I'm still Ron Abramovich, mostly retired from the NRCS Snow Survey. I'm still involved watching the rivers flow, the snowfall and rivers flow as well too. And just wanted to mainly say it's been interesting being part of the cloud seeding program and watching it grow from the early or late 1990s and early 2000s and answering some of those early questions about cloud seeding as well too, and seeing the success that it is today as well too. So just a few comments I had is it's more about the future rather than the past. So if you're looking to expand any place, I would look at cloud seeding opportunities in Idaho's salmon and Clearwater Basin should be investigated. A successful program could increase the snow water content by 10%, which will allow managers the ability to shape the hydrograph for salmon flows and may reduce or delay delivery of salmon augmentation water from the middle and upper snake reservoirs. The cold snowmelt water in the Clearwater Basin will keep rivers temperatures cooler longer and may reduce or delay the need for Dwarshak reservoir water to cool temperatures downstream. This may also allow Dvorak to remain fuller longer in the summer as promised to the locals when the dam was built. The additional water could also be used to produce additional power at Dvorak and the Columbia River dams to offset any power from any dams that may be removed. The USDR used to have a power generation software that could be used to estimate how much additional power could be used. And any additional costs could also come from BPA's Fish and Wildlife Program, as the benefits are across multiple states, not just one individual state. So thank you for the opportunity.
Okay, thank you. Okay, next I have with a checkbox, Parker, is it Cardwell?
Yes, sir.
You're from Rainmaker and you were trying to talk to me last week and I ignored you. Okay.
No worries. Chairman, members of the board, thank you for the opportunity to speak. My name is Parker Cardwell. I'm with a company called Rainmaker. We're a cloud seeding company out of Olmstead, California. The comment that I want to just touch on today is around the legislature that we're seeing pop up around the United States this year. We've seen 30 states propose legislation to outlaw two primary technologies. I believe that they're getting conflated though, is geoengineering and then weather modification. And I guess to distinguish the two initially is that geoengineering is a technology that some companies are working to employ to basically release heavy metals or heavy gases into the upper atmosphere. This is 60 to 100,000 feet. It's basically the idea that it's like sunscreen over the atmosphere to try and reduce the global temperature. Again, like we know, I guess, after a lot of the information that we've seen with Dr. Tessendorf, this is a technology that's altogether different than cloud seeding, completely different realm. But unfortunately, I think we're seeing with a lot of the lack of understanding with what's going on in the atmosphere, the terms and the technologies are becoming conflated. This year, we actually saw a similar legislature in Idaho as well. But I think as we walk through the importance of the technology of cloud seeding and the impact that water can have, it is ultimately the lifeblood of the economy and our communities in the West, but around the United States also. So luckily, just kind of a state of the union on how this legislative session has gone thus far in America is 22 states have opted to not pass or fail the legislative, the bills that have been proposed. 7 states are still currently pending the review. We likely think that the remainder of those will fail also. One state that will opt to pass it is going to be Florida. Fortunately, I think public opinion kind of came in and took a kind of a behavior of its own. But we've been very fortunate to speak with a lot of these legislators that propose these bills directly or have been on the committees that are hearing them. And I think that they've all been incredibly amendable to the technology, or at least very amicable in understanding what is being done with cloud seeding. And I think forums like this are incredibly important to understand the viability of this sort of critical technology. And members like Dr. Tessendorf and the people and the work that they're doing on the board and in the department, it's incredibly important to amplify and to just kind of walk through why we do this. The research is showing that it is safe and what the impact of that is. So kind of providing this public information availability, publicly available so that people can go through and easily digestibly read, what is being done, why is it being done, and show me why it's safe. I think the reason that we're seeing a lot of the public backlash from this is because historically this technology, not to say that it's been hidden, but maybe that we should be talking about it as we are talking about aquifer recharge programs, which is a great reason that Idaho is joining those two programs together. I think if we talk about it as like an irrigation or a water management solution, we're ultimately going to be able to kind of break through these barriers and then have a legislature that's informed more on the science and the true operations of what's going on. And ultimately, I think we'll fight through this session, and I don't think many of these states will pursue these legislation further. But I appreciate the work that we're doing here in Idaho, and I think that this can truly be the framework for how many other states, as they adopt new programs or have programs, can kind of take heed of what we're doing here and just be a little more open and transparent on how we're operating and the actions that we're going to take to enhance water. So thank you all.
Okay, thank you. And if you do want to bend my ear, I'll be here after, or we can set up another time.
Yes, sir. Okay. Thank you.
Okay, next on the list, I have Santiago Felico.
Thank you, Chairman. Thank you, Board Committee. My name is Santiago Felico, and I am a resident, a father, businessman. I was pleasantly surprised to find out that Idaho is a cloud seeding program. I've been following the technology online for the last 4 or 5 years ever since I heard about it. but for in California. And I didn't know what to expect in this meeting, so I prepared a statement that had a cover, it was basically covered by a lot of great presentations earlier. I think if I want to sum it up, and I won't go to all those things I got prepared, is to encourage the community to continue investing in cloud seeding programs. As I mentioned, I'm thankful that especially other states are, how other states are approaching the technology, a misunderstanding of the science with hesitance to really dig into it, to see how its track record is good and strong and safe. I appreciate the clear-headedness of Idaho to approach the problem with clarity, to really dig into the science. As we've seen, it has a great track record of safety, of effectiveness, and I think fundamentally all of us who are here in this meeting today love the state of Idaho is why we're here. I personally, I like to tell my friends that part of my inheritance to my children, my home is the state of Idaho, and I'm able to steward it and preserve it. And I'm encouraged to see clear thinking around how to develop state sovereignty when it comes to not just our land, other great natural resources that we have, we have the state, but certainly the treasure that we have in the water that the state has. So my comment is simply one of encouraging to thankfulness to the board and to the committee, to everybody involved in this program for tackling the science head on directly, clear-headedly, and to continue that great work. So thank you very much.
Okay, thank you. Well, next I have Sarah Alstott. Welcome back, Sarah.
Yeah. Okay, well, I'll be the first person to say that I'm against cloud seeding. My name is Sarah Alstott. I'm here representing myself and a lot of people who are, I guess, more critically looking at the science and doing more research into what assessments have been done. And the GAO report was available. It was never mentioned today. And unfortunately, it's the most current evaluation on where we're at with cloud seeding. So it's mind-boggling why we can't bring that up. It was brought up in, I think, the September meeting, but we're just not going to mention it because it doesn't show favorable outcomes for cloud seeding. I don't understand that. But I'll read what I have prepared here. And I want to thank you for taking public comment. A few of my issues here are that the cloud seeding program is experimental. It has little oversight, no public consent, no notification, no robust reporting, and less transparency than ever. The public is looking for answers, and Idaho Power no longer provides generator coordinates on NOAA reports. In a year that we were asking for more transparency, we got less. And number two, special liability exemptions for IDWR contracted cloud seeding operators after the passage of HB 266 of 2021 was a red flag for the claimed safety of the program. If safe, why liability exemptions? Risk is placed on the public as public funds are used to operate the program. Furthermore, Mr. Gibbs indicated that he was not aware of the GAO assessment findings where risks were noted. Mr. Gibbs is being the floor sponsor of HB 266 and now the committee chair of the cloud seeding program raises questions around bias and questions around his not keeping up with industry reports. Number three, previous MSDS forms show many components and flares, including aluminum. We saw over and over silver iodide. What about the other components and flares? The updated forms that people are getting now from the cloud seeding flare manufacturers are proprietary ingredients. Continued lack of transparency and no DQ oversight, but a reactionary approach is not acceptable. A microbiologist local warned, we know that no good will be done for the environment when they add particles out of their natural environment. Experiments cannot really be carried out accurately with so many variables in nature. All that can be done is to see what damage has occurred after the fact. then it is too late. Putting preponderance of evidence on those concerned creates a stalemate, and those proposing or doing the deeds should be the ones to prove the safety before application. Knowing what silver iodide by itself does in biological life in the laboratory, known for eons, should be enough to halt any such program, since all life on Earth is interdependent. And I do have those two MSDS reports to show that before we were able to see that less than 30% of the flare was comprised of 3 different components, one of those being silver iodide, and aluminum being in part of the 70% makeup. So why are we only talking about silver iodide in all of these slides? Lastly, the issue with many components within flares are now categorized as trade secrets. This is not transparent. And the geo assessment further confirms that silver iodide is nearly insoluble in water. However, when it dissolves, it releases a small number of silver ions. In high enough quantities, silver ions, a known antimicrobial substance, could have harmful effects on beneficial bacteria in the environment and water resources. Other potential seeding agents, liquid propane, and chemical salts and biological agents are less widely used. However, Idaho's using liquid propane. Idaho has become testing grounds for the experimental program, and the public is wanting answers. As the geo assessment summarized, quote, when uncertainty was considered in estimates of cloud seeding effectiveness, the estimated effect was not distinguishable from zero with a high degree of statistical confidence, end quote. A statement consistent with snowy researchers Sarah Tessendorf's comments, 24 clouds that looked ripe for seeding, but they could only draw a clear link between seeding and snowfall in 3 cases. There is a small, hard to pinpoint signal that cloud seeding created additional ice in a handful of other cases, and then no signal at all in some instances. Yet, in Idaho, we use taxpayer dollars to fund this experiment. Thank you for hearing our concerns.
Okay, thank you.
I have comments from other people that would like to, can I hand these to you?
Yes,
Okay.
just give them to Jennifer, please, if you would. Okay, that's the last person who was signed in that indicated they wanted to testify. Is there anyone else here who planned on testifying that we have not recognized? Okay, all right, thank you for your comments. We appreciate it. The next item on the agenda is committee recommendations. I'd like to ask the committee at this time, I think if there are potentially other comments coming in, it might be premature to make any recommendations until we receive all the comments and have a chance to review those. Yeah. Other committee members, what do you think?
I think that's valid, given the information we've received today.
Okay. All right. Then with that, are there any other items that the committee members would like to bring up at this time?
Mr. Chairman, I'd like to say that I really appreciate the information that's pulled together today. There's quite a bit for all of us to absorb. I agree with Mr. McMahon that we need a little bit more time to think about what we've heard today, and so I would concur in his recommendation. Take a little bit more time before we make a recommendation.
Okay. All right. And with that, if there's no other business, I'd entertain a motion to adjourn.
So moved.
Second.
Been moved and seconded. All in favor, say aye.
Aye.
Any opposed? Motion carries. We are adjourned.
Thanks, everyone.
Okay, thank you. Appreciate you taking